What exactly is a quantum? The word gets thrown around a lot. Quantum computing, quantum physics, quantum leap. But what does it actually mean? At its core, a quantum is the smallest possible discrete unit of something, not a little bit, the absolute minimum. Nature, it turns out, doesn't deal in smooth, continuous flows of energy. It deals in packets, tiny, indivisible chunks. And that one idea changed everything we thought we knew about the universe. Think of energy like Lego bricks. You can have 1 brick, 2 bricks, or 100 bricks, but you can never have half a brick. Energy works the same way at the quantum scale. It doesn't flow like water from a tap. It comes in fixed amounts, like coins rather than a continuous stream. Each one of those coins is a quantum. This wasn't just a clever analogy. It was a radical, controversial idea that upended classical physics when it was first proposed. It all started with a mystery. Why does hot iron glow? Heat up a piece of iron, and it shifts from black to red to orange to white as it gets hotter. Scientists in the late 1800s tried to explain this using the laws of physics they already had. They built mathematical models, ran the equations, and completely failed. Classical physics simply could not explain the color of glowing metal. Something was deeply, fundamentally wrong. The failure had a name: the ultraviolet catastrophe. Classical equations predicted that a glowing object should radiate infinite energy at high frequencies, especially in the ultraviolet range. Infinite energy from a piece of metal. Obviously, that doesn't happen in real life, but the math insisted it should. Physicists were baffled. Their best theories were producing absurd, impossible results. The entire framework of classical physics was cracking under the pressure of one simple experiment. Then came Einstein and the photoelectric effect. Shine light on certain metals and electrons pop off the surface. Simple enough. But the strange part? It didn't matter how bright the light was. Dim the light, nothing changes. Turn up the frequency instead. Switch from red to blue, and suddenly the electrons start flying. Classical physics said brightness should be the key. Experiments said frequency was. The two were completely at odds. Photons explained everything. Einstein proposed that light isn't a continuous wave. It's made of discrete packets of energy called photons. Each photon carries a fixed amount of energy based on its frequency. A high-frequency photon has enough energy to knock an electron loose. A low-frequency photon doesn't, no matter how many of them you throw at the surface. Suddenly, the photoelectric effect made perfect sense. Light was quantized. Energy was quantized. The quantum revolution had officially begun. So here's the core definition. A quantum is the minimum amount of any physical entity involved in an interaction, and Planck's formula captures it beautifully. E equals h times F. Energy equals Planck's constant times frequency. That tiny constant h is 6.626 times 10 to the negative 34th joule seconds. It's almost incomprehensibly small, but it is the fundamental granularity of the universe. Below that scale, physics as we know it simply doesn't apply. Today, quantum mechanics powers the world around you. Lasers, from your Blu-ray player to surgical tools, rely on quantized energy transitions. Solar cells convert photons into electricity using the photoelectric effect Einstein described. MRI machines exploit quantum spin. And on the horizon, quantum computers use quantum superposition and entanglement to solve problems that would take classical computers longer than the age of the universe. The quantum world isn't abstract. It's everywhere. That wraps up our introduction to the quantum, the smallest unit in nature. We've covered how the concept was born from a crisis in classical physics, how Einstein and Planck cracked the mystery open, and what the math actually looks like. In the next video, we'll go deeper into wave-particle duality, the strange idea that light and matter are somehow both a wave and a particle at the same time. If that sounds impossible, good. That means you're ready for it.